Okay, so just so you know, oh, yeah, okay, Blackboard. Blackboard website, well, it's got the notes for chapters 12 and 13 right now on there. But it will also have 2 practice exams Sunday night, 11:59, you know. So 2 practice midterms for the second midterm will be on there. They were ones given last year, the 2 second midterm given last year. So that'll be on there Sunday night late. Okay, now a quick review where we were in chapter 13. We had finished the first part of chapter 13, which allowed us to calculate the view factors in a thermal radiation problem, the view factors. The second part of chapter 13 talks about how we actually do some heat transfer calculations in an enclosure with thermal radiation. And we went through the derivation for 2 kinds of resistances in these problems. One is called a surface resistance. Its value is 1 minus the emissivity of the surface divided by the emissivity times the area of the surface. And there's a little model of it right there. Every surface in an enclosure has a surface resistance. Then there's a second kind of resistance called a space resistance because it depends on the space between 2 surfaces and their orientation and their geometry. Its value is 1 over A1 F12. And here's the picture that shows where that resistance is located between nodes J1 and J2. J is the radiosity of the surface. The radiosity J is what leaves the surface, the emitted radiation plus the reflected radiation. Okay, so we're looking at enclosures, and we're trying to find the heat exchange between surfaces in an enclosure. We're going to look at a specific example. It's a cubicle enclosure. Surface A1 is the right-hand side, right-hand wall. The bottom is A2, and the remaining walls are A3. So we call that a 3-surface enclosure because we're going to say the temperature of wall 3 is constant. It's given. So I'll put down what those temperatures are. So assume that we're given the temperatures in the enclosure. Let's put down what we have here. T1 is 260 C. T2, 90 degrees C. And T3 is 175 degrees C. We're going to go from the simple to the complex. So we're going to say, to start off with, let's let all the surfaces be black. So epsilon 1 equal epsilon 2 equal epsilon 3 equal 1. If the surfaces are black, you go over here, and you put epsilon equal to 1. The resistance is 1 minus 1, 0. So now we know R1, R2, and R3, 0. Don't forget that surface resistance tells you how easy it is for heat to escape from the surface by emission. How easy it is for heat to escape the surface by emission. And a black body or a black surface is the best possible emitter. So obviously a black surface has a low resistance because a lot of heat gets out. Okay, back over here. Let's see what else we might need. I think that pretty much covers that. So we're going to draw the circuit, but I'll just remind you first, the last time we met, we looked at this configuration, and this was A1, and this was A2, and the resistor model for that looked like this. And we found this, it's a series. Two surface enclosure, they're all in series. And if you want to find the Q, since all the Q's are the same, in series, Q1 equal Q12 equal Q2. The way you find the Q is you take EB1 minus EB2, which you know the temperatures are given, divided by R1 plus R12 plus R2. And now you've got Q, end of problem. The only unknown there, well, you can find the J's. They're not important to find the J's. Normally, in thermal analysis, we want to find the Q's. So that's how you find the Q's. Now we make life a little more difficult. That's a two-surface enclosure. This is a three-surface enclosure. Okay, it could be this room. The front wall's area A1. The floor is A2. And the other walls and the ceiling are combined A3. The reason why we can call them by one nodal designation is because they all have the same temperature and they're touching each other. Okay, so draw a thermal circuit like this. But now, rather than two, you've got three nodes. They're all black. Okay, 1, 2, 3. There are the three nodes. Now, I'll put them here and I'll set them equal to 0, but for right now, that's R1. This is EB1, J1, J2, R2. We'll make it a big problem, and then we'll reduce it to a smaller problem. J3, R3, one, two, 1, 3, 3, 2. Q1, Q2, Q3, Q12, Q32, it should be 1, 3, and this is Q12. Okay, so there's the full-blown three-surface enclosure. Anytime there's three surfaces, that's how you set the little circuit up, the thermal circuit up. Everything is labeled. Every node is labeled, J's and EBs. Every resistor is labeled. Every heat flow is labeled. How many heat flows are there? 6. Unknown J's, 3. Okay, now we'll take I know since surface 1 is the hottest and surface 2 is the coldest, I know heat goes from 1 to 2, of course. It's going from hot to cold. I know that since 1 is hot and 3 is colder, 1, 260, 3, 175, heat goes down that way. I know that. Over here, 3 is 175, 2 is 90. Okay, it goes that way. I know that. What I don't know is which way that Q3 is. I won't know it until I solve the problem, which way it is going to go. Okay. So let's do first things first. This is all black surfaces. All the R, 1, 2, and 3 are 0. Okay, gone, gone, gone. The new circuit looks like this. EB1, EB2, EB3. Okay. Q1, Q2, I don't know which way yet, Q3. All right, but you know what? I know those EBs. Those are known. EB1 equals sigma T1 to the fourth. Black body emissive power. Sigma 5.67 times 10 to the minus 8 multiplied by let's see here. Oh, there it is. Okay, multiplied by my temperature. 5, now don't forget, we're in chapters 12 and 13, absolute everywhere, 533 K times 533 to the fourth. EB1, 4575. EB2, it's known. EB3, it's known. $22.84. When you're doing these calculations, you can kind of take a shortcut if it helps. It doesn't save a lot of time, but sometimes it saves you making some silly keyboard errors. If you're doing this calculation right here, the easy way out, since these guys are always in the hundreds, because you add degrees C in 273, what you do is you make this 5.33 times 10 squared raised to the fourth. Then you make that 5.33 to the fourth times 10 squared raised to the fourth. And lo and behold, oh, those guys go out, thank goodness. I don't need to key that in, at least, on my calculation. So you can avoid keying in those 10 to the 8th stuff and 10 to the minus 8 stuff. Just move the decimal point on the temperature 2 places to the left, knock out the 10 to the 8th, 10 to the minus 8, and now raise 5.33 to the fourth power. It just saves some calculations in a stressful situation like an exam where you might key the wrong thing in and then all of a sudden your answers go crazy. All right, so there we are. All right. Let's call these things what they are. I'm going to move R12 inside here. Q1-2, Q1-3, Q3-2. All right, let's find Q1. Q1 is equal to, what comes in goes out. Q12 plus Q13. Q12, EB1 minus EB2 divided by R12. Okay, now I need the R's, okay? So, next step, I'm stuck here until I find, I'll put them both on here, plus EB1 minus EB3 divided by R13. Okay, so I'm going to find the R's. I think I need all that board space over there, so I'll put the R's over here. From figure 13.6. Two rectangles with a common edge at right angles, A1 and A2. F12 from that figure, 0.20. Okay, So I've got R12 is F. I'll put them down here in a minute. I'll put it down here. Are you okay with that? Okay. R12 equal 1 over A1 F12. I'll put them down here. A1 equal 3 meters squared, 9 square meters. A2 is the same, 3 square meters, 9. A3, there's 4 remaining surfaces. Each one is 3 squared, 36 square meters. Okay, there's the areas. Put them in here. That resistance, 0.556. 556. I need R13 and R23. Okay. So I need F13. F11 plus F12 plus F13 equal 1. Enclosure law, energy balance. Surface 1, plane surface, F11 is 0. Surface 2, a plane surface, F22 is 0. Surface 3 is not plane. F33 is not equal to 0. F33, not 0. Okay, so F13, 1 minus 0.2, 0.80. R13, 1 over A1, F13. Put it in there, 0.139. By symmetry, looks to me like F13 is the same as F23. Of course it is. F13 is the same as F23. It's a cube, symmetrical, 3 by 3 by 3, all the sides are equal. So of course it's the same. Conclusion? Oh, then that must mean R23 is the same as R13. Yeah, it is. So now I've got them all. I've got R12, R13, and R23. Don't forget that if I want to, well, I'll write down R23. Don't forget reciprocity. A2 F23 equal A3 F32. Conclusion. It doesn't matter the order of the subscripts because of reciprocity. R23 equal R32. R21 equal R12. R13 equal R31. It doesn't matter. You say, you know, how come you call that Q32 and that R23? It doesn't matter. If you don't like that, call it R32. It's the same number. Why? Reciprocity. Okay, what do I know? I know it, 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 I know it. I can solve it. I can do the same. Well, I better put it down to show you. Q2 equal, here's Q2. It's going out. What comes in? Q12. What comes in? Q32. Okay. EB1 minus, we have that, yeah, 1 to 2. Got it. Okay, the last one, Q3. What comes in? Q13 what goes out, minus sign Q32. Minus so there, how many different Q's are there? There's six different Q's. You want to find them? There they are. They're all right there. Here's Q12. Here's Q13. Here's Q1, and so on and so forth. You can find all 6 Q's. Now, to see which way the heat's flowing down here, look at this thing right here, this calculation. If Q3 is negative, you guessed wrong, okay? Okay, because this equation right here will tell me which way this Q is, positive or negative. If this number here is big compared to that number, it's a negative sign. What is this? This is what's coming in. What is this? It's going out. Okay, so that's how you tell which way Q3 is. Okay, if 5 watts comes in and 3 watts goes out, 2 watts have to go down. That way, that way. So once you find Q13, Q32, that's the game you play. This comes in, that goes out, this takes care of the rest. That makes it equal sign. Okay, black surfaces. All right, so now we've got black surfaces. Obviously, in the real world, there's not too many problems where all the surfaces are black. Generally, they're not black. So our next step is non-black surfaces. Okay, no more of that equal to 1. Don't put them equal to 0. I'll put the picture here. No, do the work over there. All right, so now we have, again, the same thing. Except now they're not 0. You know, you might say, when you wrote this down here, EB1 minus EB3 divided by R13. Okay, the 1 comes first, the 3. Why didn't you make that R32? Well, first of all, because I know reciprocity, R32 is R23. Well, which one do I want to find back over here? Do I want to try and find first R32 or R31? Oh my gosh, no. I don't want to find R31 first. I want to find R from the small surface to the big surface, R13. So I find R13 first. There it is right there, R13. I don't want to find R31. So my conclusion is, you've got a choice to make to find these R's, the 2 subscripts. Take the easy way out. Sometimes one is easier than the other one to find. Maybe F23 is easier to find than F32. Then use the R23. Take the easy way out sometimes. Look at them. There's 2 possibilities to find the view factors. Flip the subscripts. See which one's easier to get. And you'll see in homework that that works out sometimes that way. There's a hard way, there's an easy way. On a timed exam, there's 2 ways to do it sometimes, easy and hard. You want the easy way out, the less time-consuming way out. Okay, now, put the resistors in. pretend I don't know which way the heat flows, because for more complicated problems, I'm not going to know which way the heat flows. There, I used my intuition for the direction of the arrows. Let's assume you don't use your intuition here, and you just want to solve for the Q's. I don't know which way the Q's are going. So here's what you do. You go to equation 1321. In the book, and I'm going to write it for node 1, node J1. This is what it says. The heat that comes into node J1 from the surface 1 goes out to nodes J2 and J3. All right, so the heat that comes in to node J1, EB1 minus J1, divided by R1, that's Q1, equal the heat that goes out to J2 and J3. Okay. I'll draw a little picture down here to show that. So there's the picture. The heat that comes in to node J3 from the surface 1 goes out, some to surface 2, some to surface 3. Are those directions right? I don't know. I'll find out when I'm done if they're right or not, but for right now, that's what you say. Now you write the next equation for node J2. Here's what you say. The heat that comes in to node J2 from the surface, that's up here, some goes to J1 and some goes to J3. Okay. EB2 minus J2 divided by R2 equals some goes to node 1. Some goes to node 3. I'll draw the picture down here. What comes in from surface 1, A1, goes out either to 3 and to 1 that way. That goes with that picture. Now I do node J3. Node J3, the heat that comes in to node J3 from surface 3 goes out to 1 and 2. Okay, to 1 and 2. Here's a picture. Put a check mark by everything you know. What's left? Solve for it. Okay, J1, J2, and J3. very similar to your next computer problem in class. It's going to be a 6-surface enclosure like this room. There's going to be possibly 6 different temperatures of the walls. Each wall has a different temperature. You'll write. You won't know which way the heat goes from where to where. You can't guess it. Don't try and guess. I think the heat goes from that wall to that wall. No, it's not that easy. You can't do it that way. Don't even try and guess. Play the mathematical game. For every node, if there's 6 surfaces in this room, there's 6 different nodes. There'll be 6 different J's. You'll solve them, whatever method, Excel, MATLAB, TI-89, whatever it might be, and get the 6 J's. Once you got them, if somebody says, what's Q1? There it is. What's Q23? There it is. What's Q13? There it is. So once you know all the J's, you can find any of the Q's in the problem. And how many are there again? Q1, Q2. I don't know the directions, you'll find out. It depends on Q3, Q13, Q12, Q23. There's 6 of them. 6 of them, okay? You can find them. Here's Q1, okay? Here's Q2, here's Q3. Here's Q12. Here's Q23. Here's Q31, or Q13. There they are, all the Q's. That's what you want to find typically in a thermal analysis, all the Q's. Okay, so the easy one, all the surfaces are black. Look at the picture. By the way, just so you know, are there any J's? No, there's no J's. When they're not black, are there J's? Oh yes, there'll be the J's now, the radiosities. They're the unknowns. Okay, over here, all black, no J's. By the way, when I got rid of that resistor, why did I replace that J1 at that node with EB1? Sometimes that confuses people. Well, let's go back and ask you a trick question from simple circuit theory. V1 equal 10 volts. The resistance here equal 50 ohms. This is V2. This is 100 amps. And somebody tries to trick you, and they say, oops, pardon me here. This resistance right here is 0, not 50. You say, okay, what is V2? Now, look here. This is like V1, I know it. This is like J1, I don't know it. The resistance is 0, yep. Is there a heat flow Q1? Of course there is, it's right there. So somebody says, what's V2? God, you say, hey, come on, don't try and kid me. V2 is 10 volts. What else can it be? What else can it be? It's got to be 10 volts. There's no losses. Resistance is losses. So if there's no losses, the voltage didn't change. Right. If R1 is 0, then these two guys have to be equal. That's how it works. Okay, that's how it works. So I put the EB1, the J's disappeared. In the real world, many surfaces aren't black. Now comes a tougher problem. Here it is. How do you do it? Mathematically, this way, okay? So we've worked 2 problems so far. Now the third problem, same picture, everything's the same, except now I say, you know what? Surface A1 is still 260, surface 2 is still 90, but now surface 3 is adiabatic, perfectly insulated. Adiabatic. What does that mean? Well, I know what adiabatic means. It means Q3 is 0. Adiabatic. Let's assume that they're all black. All surfaces black. Did the EBs change? Of course not. Did the resistances change of R1, 2, R13, and R23? No. Are these guys all 0 now? Yeah, they're all black. Okay, 0. Okay, here's my picture now. There's my picture. Same picture, you see, same picture, except for one very important thing. He's 0. No heat flows that way. So guess what happens? When Q13 comes down here, it's equal to Q32. Okay. Here's a new picture. This is what I say to myself. I say, you know what? Here's how the heat flows. It comes in Q1, it divides, some goes down, some goes straight across. Here comes my fingertips. Uh-oh, back together again and out. Parallel, parallel. When you do this, they come here, they split, they come back here and go out. That's parallel circuit. All right, so now we have a parallel circuit. Comes in like this. Some goes this way. Some goes this way. And then goes back out. Here's the nodes, EB1. This is Q1. This is EB2. This is Q2. This is R12. This is R13. This is R23. This is EB3. This is Q12. This is Q13. This is Q32. So there's the simple thermal resistance model that you want to work with. It's a parallel circuit. If it is, I can tell right away that Q1 equal Q2. What comes in must go out. Because it can't get out 3, it's adiabatic. Okay, parallel circuit, you want to find Q1? All right, Q1 equal EB1, the big value, minus EB2, the low value. Divided by R equivalent. R equivalent for what? A parallel circuit. Multiply the two branch resistances together. Divide it by the sum of all the resistances in the two branches. Got it. I know every value there. I can find Q1. I can find Q2. If you want to find Q13, it's equal to, I'll put it down here. Q13 is the same as Q32. That's equal to EB1 minus EB3 divided by R13. I know EB1, I know EB3, I know R13, I got it, that's Q13. I can find any Q term you want me to. There's 6 of them. Q1, Q2, Q3. Q12, Q13, Q23. I can find all 6. Do I see a J anywhere? Nope. Why not? The surfaces are all black. J's not going to come in this problem. We've worked 3 problems now. Now comes the 4th one. You know what's left. All right, this was when all the surfaces were black. Now all the surfaces are non-black. None of the resistances are 0. Leave them all in there. All right, I'm going to clean this guy up here, I think. Got it, got it. Okay, let me add one here. Okay, there's the picture now. Assume I don't know which way those cues are going. Now, we're going to, again, assume we don't know which way the cues go. In a simple problem like this, we pretty much do, but we're going to play the game of using the equations 13, 21 and pretend we don't know which way the cues go. Okay. If you want to do it by this method, you can. All you do is you put a resistor here, R1, EB1, J1, J2, R2, Q2, now it becomes a series parallel circuit. Series parallel circuit. Simple to solve, not a problem. Do it very easily. But we're going to show you how you can also use the equations besides looking at solving it with the graphical picture of what's going on, the thermal resistance network. Okay, but you can do it by looking at this simple picture here and doing a series parallel circuit. You know, all you've got is 2 more resistors here. We'll go ahead and do it. R1 plus this plus R2. There's the answer right now. That's all you do. Very simple. Series parallel. Okay, but when you do this kind of problem for your computer problem for homework, there's going to be 6 surfaces. You don't want to do it this way. No, it's a bear. You don't do it this way. You're going to do it this way and have equations to solve. For what unknowns? The J's. Where are the J's? There they are. J1, J2. Do I know them? No. All right, node J1. Here's the rule again. When you write the nodal equation, what comes into the node J1 from the surface is EB1 minus J1 divided by R1. There. Equals what goes out? J1 minus J2 divided by R12. Yeah. Plus what goes out? J1 minus J3 divided by R13. There. Got it. That checks. Node J2. Here it is. Same thing, this equal this plus this. We've done it before. Now here comes a change. Node 3 no longer looks like this. Node 3 has something that looks like this. Okay, so now we change the node 3. This is equation. This is equation. Now we use equation 1322 for node 3. Why? Because it says in the book that if the node has a specified heat flux, then use equation 1322. You don't use this anymore, you do this. If a node has a specified heat flux or heat transfer, then that's the equation you want to use. What did our problem say? Our problem said surfaces 3 are adiabatic, which means Q3 is 0. So now we put the 0 over here. Okay, there they are. 3 equations. Linear, simultaneous, whatever method you want to do. Solve for what again? You don't need J3 because I know J3. How do I know J3? Look at the picture. J3 equal EB3 because there is no, by the way, oh, that was for black surfaces. If it's non-black, it looks like that. If Q is 0, then I know that J3 equal EB3. Okay, so I know that. Okay, got them all. Now, what do I do with them? All right, how many Q's are there? There's 6. Let's do the easy one first. Q3 is 0. Okay, good. I want Q1. There it is. I put J1 from there into there. I know R1. I know EB1. They're over there. I solve it. Q1. I want Q2. There it is. I want Q1, 2. Take your choice. Now, watch the sign. If J1 is bigger than J2, that means heat goes from J1 to J2. Now, J1, 3. If J3 is greater than J1, J3 greater than J1, then heat flows that way. So by looking at that, you can tell, comparing the J's, you can tell now which way the heat flows. The heat flows from the high J value to the low J value. Not so important in a 3 surface enclosure. But a 6 surface enclosure, this room, oh yeah, it helps dramatically. You want Q23. There it is, Q23. 2, 3, right there. This is Q32, same thing. One sign's negative, one sign's positive. So what have you found? 6 Q's. Done, you're done, that's it. So you write the equations like that. So that's our 4th problem now, okay? First, just to review, the first problem was I know all 3 temperatures, T1, T2, and T3. All surfaces are black. I showed you how to solve it. Next problem, 3 surfaces, 3 known temperatures, but they're not black. We solved it. Next thing, 2 surfaces, known temperature. Other surfaces, adiabatic. Okay, all black. We did it. The last one, 2 surface temperatures given. 1 surface, adiabatic, non-black. There it is right here. And there's not much more you can do in a 3 surface enclosure. I just about covered everything on that. Now, here's what you don't want to do. Let's take this room where there are 6 different surfaces. Maybe temperatures are known on a couple of them, many of them. Maybe Q is given. Maybe it says the heat into surface 1 is 1,000 watts. What does that mean? Well, that means that outside this box, there might be some electrical heating elements on this outside surface. And then these guys go to some kind of voltage supply and they heat the outside the box. If somebody tells you that they're heating this with electrical wires that put out 1,000 watts, and it's insulated on the top of that then, that 1,000 watts has to go in the box, in the enclosure. Okay, that's my Q. That's my Q1. Now I know Q1. Q1 is 1,000. So I use equation 1322, where I see Q1, I put 1,000. That's a known heat rate, a known heat rate. Okay, so let's say that you're doing this room with the 6. Okay, so here we have, this is J1, this is J2. J3, I better change that. This is J1, EB1, J1, EB2, J2, and so on, and so on, and so on. 3, 4, 5, 6. This is R12. This is R16. This is R13, R14, R15. This is R21. This is R23. This is R24. This is R25. This is R26. Oh, you keep going? Looks like somebody built a plate of spaghetti on the floor. You think, oh my gosh, what's going on? Which way is the heat flowing there? This is really confusing to me. I don't see what's going on here. You're right, which means that this approach of the equivalent network doesn't work very well for more than 3 surfaces. It gets too confusing. It's not worth too much. Then what do? Fall back on the math, because it's not going to fail you. There they are. There they are. Now you can do it. Draw a new picture. EB1 to J1 to J2 to J3 to J4 to J5 to J6. Bam, done deal. Write the equation. Write all 6 of them. Solve them simultaneously for what? The J's. Once you get the J's, then what do? You put them in the Q equations. Here's Q1, Q12, Q13, Q2, Q3, Q32. Put the J's in. Done. Okay, so we don't use these circuits for any more than 3 surfaces. And it's more to give you a visual graphic feel for the problem, if it helps you that way. That's all it is. It sometimes helps people to see for 3 surfaces how the heat might be flowing. But when you try and draw this, it's pretty much worthless to try and analyze it that way. Extremely difficult. So fall back on the equations. Okay, this is a good stopping point. We're going to finish up chapter 13 on